This video will highlight a promising new post-tensioning technology of electrically isolated tendons. Electrically isolated tendons, or EITs, are pre-stressed tendons in which the pre-stressed steel is electrically isolated from the surrounding concrete over the entire tendon length, including the anchorages. EITs have several advantages. EIT technology allows bridge owners and DOTs to validate full encapsulation of a post-tensioned, or PT, tendon, validate proper installation of a tendon encasing system, and provide long-term monitoring if desired. Let's take a closer look at EIT technology. Here we see an encased EIT anchor with a grout cap. Let's strip away the concrete around the EIT anchor, revealing reinforcing surrounding the anchor. Stripping away the reinforcing and removing the grout cap provides a clearer view of the EIT anchorage. Removing the wedge plate, we now see the unique EIT components: the plastic trumpet, the isolating plate, and the cable. The plastic trumpet and isolating plate provide a highly electrically resistant barrier that isolates the PT strand from the electrically conductive metallic tendon components. The cable is used to facilitate electrical resistance measurements that will verify electrical isolation of the PT strand. Electrical isolation is provided over the entire tendon length. Let's take a moment to see what is connected between our anchorages. Moving to a larger X-ray view of our bridge, we can see a section of tendon within the bridge. The tendon uses a highly electrically resistant material for the duct and duct connector. The duct connector shown also includes a plastic grout vent tube and screw cap. Taking a closer look at the post-tensioning duct, we see that plastic half-shells are used when the tendon is in contact with reinforcing steel. All of these components are detailed to encapsulate the tendon and to provide electrical isolation. The EIT system does not stop there. It also includes components that facilitate electrical resistance readings between the PT strand and its surrounding concrete. These electrical resistance readings are used to validate that the tendon is completely encapsulated. Let's look at these components. Returning to our below-deck view, we can see an anchor with a grout cap connected to a junction box. The wire extending from the grout cap provides an isolated connection to the tendon's pre-stressed strands. This wire is then secured to the concrete wall and then connected to a junction box. The junction box has 3 wires, one wire connected to the pre-stressed tendons, labeled the main lead, and 2 connected to the bridge's reinforcing steel, labeled as redundant connectors. If we strip away the concrete, we see that the 2 wires exiting the junction box at the top are connected to the reinforcing steel. The independent connections to the reinforcing steel and pre-stressing strand provide the opportunity to measure the electrical resistance between these 2 steel components. The reinforcing steel, PT strand, concrete, and PT grout will all conduct electricity with minimal resistance. Therefore, the measured resistance between the PT strand and the reinforcing steel is directly correlated to the protection provided by the highly electrically resistant duct and its ancillary components. Any defect in the PT tendon encapsulation will allow electrical current to pass and consequently lower the electrical resistance of the system. Returning to our junction box, we connect an LCR meter to supply the electrical current and measure the resulting resistance of the embedded EIT. A black wire connects the LCR meter's negative connection to the junction box's blue or lower main connection, which is connected to the PT strand. A red wire connects from the LCR meter's positive connection to the junction box's white or middle redundant connection, which is connected to the embedded reinforcing steel. The upper gray wire provides redundancy in case of a poor connection with the white wire. Let's take a reading. The LCR meter reading shows 1,000 kiloohms of electrical resistance. If, for example, this is a 50-foot tendon, this reading demonstrates a perfect encapsulation of the tendon, meaning that there are no defects in the encapsulated tendon. We have our perfect encapsulation reading, but what does it mean under the surface? Let's return to our X-ray view of the encapsulated tendon to see what is meant by perfect encapsulation. If we were to cut into the tendon, we would see that the duct is properly grouted and there are no defects or damage to the duct. This perfect encapsulation allows the electrical current to uniformly pass through the highly electrically resistant duct. EIT technology also reveals defects. Returning to our junction box and LCR meter setup, let's take another reading. In this scenario, the LCR meter reading shows 7.5 kiloohms of electrical resistance, which is much lower than the previous reading. What does this mean? This low reading indicates an issue. Returning to our X-ray view of the duct, we see there is a crack in the black plastic duct, which is highlighted by the red box on your screen. Let's return to our X-ray view of the encapsulated tendon to see what happens between the electrical current and the duct when there is a perforation in the duct. Here we see the electrical current flowing into the tendon. Notice that where the perforation is in the duct, a large arrow appears, flowing further into the tendon. The number and size of duct perforations have an influence on the electrical resistance. The larger the size of perforations and the higher their number, the lower the measured resistance. This has been an overview of EIT technology. For more information on this technology and concrete bridges, visit the FHWA Bridge website, https://www.fhwa.dot.gov/bridge/concrete.